let's look at simplifying some expressions involving our sum and difference identities. In this first example, we want to evaluate the expression cosine of 105 degrees. Well, without using technology, we're going to have to resort to using the unit circle. But unfortunately, 105 degrees is not one of our unit circle angles. All right, it has a reference angle actually of 75 degrees, and in order to use the unit circle, it needs to be 30, 45, or 60 degrees. So right now, with what prior to what we've studied in this lesson here, we don't have enough information to do this with just the unit circle. But with our sum and difference identities, we can. Okay, so to do that, we need to be able to think of 105 degrees as the sum, or the difference, but we'll do sum this time, the sum of two angles that are unit circle values. Okay, so for example, I could think of 105. Let's kind of write that down here. Some different options. I could think of as 105 degrees as 45 degrees plus 60 degrees, right? So that would be a sum. I could also think of 105 degrees as 150 degrees minus 45. So I could do this either as a sum or a difference. It doesn't actually matter. You'll get the same answer either way. Okay. Since both 45 and 60 are unit circle values in the first quadrant, let's go ahead and just do that. Okay. So I'm going to rewrite the cosine of 105 degrees as the cosine of 45 degrees plus 60 degrees. Both 45 and the 60 are still in the same cosine expression. So this is not cosine of 45. So this is not the cosine of 45 degrees plus the cosine of 60 degrees. Okay, that's not what we're doing. Okay, I'm just saying I've taken that 105 and broken it apart as the sum of two values, the 45 and the 60. It's still within the same cosine. Okay, now I know that from our identity, the cosine of A plus B has to equal the cosine of A times the cosine of B minus the sine of A times the sine of B. So that's what the identity for cosine of A plus B looks like. So I'm going to apply that here. In this case, the A is that 45 degrees and the B is the 60. So that means I could rewrite the cosine of 45 plus 60 as the cosine of 45 degrees times the cosine of 60 degrees. That's the cosine A and the cosine B, minus the sine of 45 degrees times the sine of 60 degrees. That's the minus sine A sine B part. Okay, so I've just taken the cosine of 105, rewritten it as the cosine of 45 and 6 plus 60, and then used our identity to rewrite that as these separate trig functions. And so if you notice, the 45 and the 60, cosine of 45, cosine of 60, sine of 45, sine of 60, those are all values that we can compute using our unit circle. Okay, so I know the cosine of 45 degrees is a square root of 2 over 2. I know the cosine of 60 degrees is a half. So we have square root of 2 over 2 times a half minus, well, sine of 45 is also a square root of 2 over 2. And the sine of 60 is a square root of 3 over 2. So I have square root of 2 over 2 minus times a half minus a square root of 2 over 2 times a square root of 3 over 2. Okay, so we've already actually done all the technical stuff. Now it's just a matter of simplifying our answer. Okay, so what is the square root of 2 over 2 times a half? If you multiply the numerator, square root of 2 times the 1 is a square root of 2. Multiply the denominators, 2 and 2 make 4. All right, then we do minus, we have square root of 2 times the square root of 3, which would be a square root of 6. And then we have a 2 and a 2, which gives us a 4. So we have the square root of 2 over 4 minus the square root of 6 over 4. And we could combine that into a single fraction if we want. So we have the square root of 2 minus the square root of 6, and all of that is over 4. So that is the exact value for the cosine of 105 degrees. All right, what if we tried doing sine of 5 pi over 12? So again, 5 pi over 12 is not one of our unit circle angles. So can I write 5 pi over 12 as the sum or the difference of two other values that are? Okay, so I could take 5 pi over 12 and I could rewrite it as maybe 4 pi over 12 plus pi over 12, right? Because 4 pi plus pi is 5 pi. Well, that 4 pi over 12 actually would reduce down to pi over 3, but pi over 12 doesn't. It's just going to be left with the pi over 12. So the pi over 3 is actually a unit circle value, but the pi over 12 is not. Okay, so using pi over 4, or 4 pi over 12 plus pi over 12 isn't going to help us. We need both values to reduce down to unit circle. So another way we could try this would be 5 pi over 12 would make that equal to 3 pi over 12 plus a 2 pi over 12. Do both of those reduce down to something that's looks like a unit circle value? Well, 3 pi over 12 would reduce down to pi over 4, and 2 pi over 12 would actually be just a pi over 6. So both of those, pi over 4 and pi over 6, are values that we see on the unit circle. So rewriting 5 pi over 12 as 3 pi over 12 plus 2 pi over 12 is going to work for us. Okay, so let's go ahead and do that. We have sine of 5 pi over 12. I'm going to rewrite that as the sine of 3 pi over 12 plus 2 pi over 12. Again, both of those fractions are inside the same sign. We didn't separate it into two signs. And then we can go ahead and simplify that. This will become equal to the sine of pi over 4, that came from the 3 pi over 12, plus a pi over 6, that came from the 2 pi over 12. So this is now in the form of sine of A plus B. From our identity, I know that that is equal to the sine of A times the cosine of B plus the cosine of A and the sine of B. So I'm going to take that identity and I'm going to replace the A's and the B's with pi's over 4 and pi's over 6. So we're going to get this is equal to the sine of pi over 4, because that's my A, times the cosine of pi over 6, because that's the B, plus the cosine of pi over 4 times the sine of pi over 6. And these four expressions, those are all unit circle values. I know that the sine of pi over 4 is a root 2 over 2. The cosine of pi over 6 is going to be a root 3 over 2. I know the cosine of pi over 4 is a root 2 over 2, and the sine of pi over 6 is a half. So I have the square root of 2 over 2 times the square root of 3 over 2 plus root 2 over 2 times a half. And we saw this very similar in the last example. We're going to get a square root of 6 over 4 plus a square root of 2 over 4, which I could rewrite as a square root of 6 plus a square root of 2 all over 4. And so that is the exact value for the sine of 5 pi over 12. All right, let's try another example here. This time we have a longer expression. We have the cosine of 145 degrees times the cosine of 35 degrees minus the sine of 45 degrees times the sine of 35 degrees. Well, if you look at this at initially, the 145 and the 35 degrees, those are not unit circle values. Okay. But this does look like it has the form of cosine A cosine B minus sine A sine B, right? As I write that out, the cosine minus sine format matches, that pattern matches. And in both sides, both cases, the A corresponds to the 145 degrees and the B corresponds to the 35. Okay. And so I know this is one of our sum and difference identities for cosine. This is going to equal the cosine of A plus B. Okay, so to use that in our example here, we can rewrite the cosine of 145, cosine of 35, minus the sine of 145, sine of 35, as just a single cosine expression that contains A plus B. So it's going to be the cosine of 145 degrees plus 35 degrees. And that's all within the single cosine. If we go ahead and add those together, 145 plus 35 is going to be 180. So we have the cosine of 180 degrees from the unit circle. Again, that would be sort of on the left side of the unit circle where it hits the x-axis, and that is an x value of a negative 1. So cosine of 180 degrees is a negative 1. All right, let's try one more example. This time we're going to combine our trig functions with some inverse trig functions. So we have the tangent of the quantity inverse sine of 12/3 minus the inverse cosine of 3/5. Okay, as we look at that, that might be really confusing. We have tangent functions mixed with some inverse functions, but we've done that sort of stuff before. But now we have two of them inside, and they're being subtracted. Okay, so when I see this inverse sine of 12/3, remember what happens, what kind of value are we getting when we compute an inverse sine or an inverse cosine? Whenever we compute an inverse trig function, the result is always an angle. So think of this inverse sine of 12/3 as some angle A, and think of the inverse cosine of 3/5 as some angle B. That really just means that we're looking at the tangent of A minus B. And our identity for the tangent of A minus B is that we get the tangent of A minus the tangent of B, all divided by 1 plus the tangent of A times the tangent of B. Because this is written in terms of A's and B's, you might be thinking, how do we find what A and B are? But I actually don't need to ever truly find the value of angle A and angle B. I just need to take the tangent of A and the tangent of B. So that means, again, we don't need to find the angle, we just need to know what the tangent is. And so if we go back to our right triangle trig, we know that inverse sine of 12/13 would correspond to us saying the sine of A is equal to 12/13. And if you remember, the sine of an angle is the opposite over the hypotenuse. So I could draw a right triangle with an acute angle A, and the opposite side would have a length of 12, and the hypotenuse would have a length of 13. And so that means I can use the Pythagorean theorem to figure out the missing side. So a squared plus 12 squared has to equal 13 squared, which means we have a squared plus 144 equals 169, which means a squared is equal to 25. So a is equal to 5. Okay, so if a is equal to 5 now, I can figure out what's the tangent of a. That means the tangent of a is going to equal 12/5, right? Well, what about b? Okay, so I know that the inverse cosine of 3/5 means that I could think of this as the cosine of angle B has to be 3/5. Cosine is the adjacent over the hypotenuse. So again, I could draw another right triangle with acute angle B, The adjacent side has length 3. The hypotenuse has a length 5. And so we can, again, do Pythagorean theorem. So 3 squared plus b squared has to equal 5 squared. 9 plus b squared has to be 25, which means b squared has to be 16. So b has to be 4. So I now know all three sides of the triangle, and that means that I can figure out what is the tangent of b. Now, tangent is the opposite over the adjacent, so 4/3. That gives me everything I need. Okay, I know the tangent of a minus b is equal to the tangent of a minus the tangent of b, all divided by 1 plus the tangent a tangent b. So I can rewrite this tangent of inverse sine of 12/13 minus the inverse cosine of 3/5 as the tangent of a, which we said was 12/5, minus the tangent of b, which we said was 4/3, divided by, so all of that is divided by 1 plus the tangent of a, which we said is 12/5, times the tangent of b, which is 4/3 again. Okay, all that's left from here is simplifying out the expression. Okay, in the numerator, to combine 12/5 with 4/3, we need a common denominator, which is going to be 15. So multiply 12/5 by 3. That'll give me 36 over 15. I need to take the 4/3 and multiply it by 5. So that's going to be 20 over 15. So 36/15 minus 20/15 divided by 1 plus, well, if we multiply 12/5 and 4/3, we're going to get 48/15. And I could go back and replace this 1 with a 15 over 15. So everything is now written with common denominators. In the numerator, 36/15 minus 20/15 is going to be 16/15. And 15/15 plus 48/15, 48 plus 15, 48, 58, 63. So we're going to have 63 over 15. So how do you take 16/15 and divide it by 63/15? You multiply the reciprocal. So this is going to be 16/15 times 15 over 63, which the 15s are going to cancel out. And so we're going to be left with 16 over 63. Okay, so the tangent of the inverse sine of 12/13 minus the inverse cosine of 3/5, without actually figuring out what those inverses actually are, we are able to say that that is equal to 16/63.